Hello. Um, Yesterday I handed out this chart to everyone in class. So um, while you're watching this video, get out that chart as you're watching, and you can fill in the the different rectangles yourself as you're watching this video. Um, so this chart is a nice way to summarize all the main formulas and etc. that you need for inferential statistics, which is chapters 14 through 21 of our textbook. So let's start here with the chapter. So we'll start with chapter 14 and 15. Those two chapters are the same situation. Chapter 14 is confidence intervals. Chapter 15 is hypothesis testing. So this was the very first situation where you first learned how to do confidence intervals and hypothesis testing. And the basic situation here is you're assuming a normal population, and also you're assuming that sigma is known, that's the population of the standard, excuse me, the standard deviation of the population. Um, and if under those two situations, then that's when you use the stuff you learned about in chapters 14 and 15. Now, what are the conditions? Under what conditions is it okay to use uh, sorry, one more thing. Under situations, we have one sample as opposed to some other chapters where we had two samples, and the variable is quantitative. Because in some chapters we have quantitative variables, in other chapters we have categorical variables. So quantitative, so we're dealing with the raw data is measurements, like the measurements are all in centimeters or in milligrams or something like that. Okay, so what are the conditions? The only new condition I would add here is uh, the um, the samples must be simple random samples. Um, Now, sometimes in the homework we just pretend it's a simple random sample, but in real life you should have simple random samples in order to um, validly use these techniques in chapters 14 and 15. And then besides that, also sigma must be known, and we assume a normal population. Now remember that in real life you're not going to know sigma, and so this first uh, chapter 14 and 15 is for just learning how the process goes, because it's the simplest one. Okay, the population parameter is mu. That is the particular thing we're interested in. Whenever you're doing a hypothesis test, you're testing a claim about mu. If you're doing a confidence interval, you're trying to estimate what mu is. And that, of course, is the population mean. You can put that down if you forget what mu stands for. So population mean. All right, so sample statistics. Once you get your raw data from your sample, what do you need to summarize it? Well, you need x bar and you need n, and then you'll use those for future calculations. You don't need s, not yet, because we're assuming we know the population standard deviation. Okay, so what is the standard deviation of the sampling distribution, or in other words, what is the standard error? In this case, it's sigma over square root of n, because sigma is known, and so that actually is the exact standard deviation of the population. We don't have to estimate it. It's the actual standard deviation. And what that means is if you have millions and millions of different x bars, because this is a random variable, this x bar, if you have millions of x bars and you make a histogram out of all those possible x bars you could get, it turns out to be have the standard deviation of sigma divided by square root of n. Okay, what is the sampling distribution? Well, it's a normal curve. Remember, in some chapters, the sampling distribution is a t-distribution, but in this case, it's a normal distribution. Okay, what table do we use? In our textbook, it's table A. That's the table with all the normal curve areas. Or if you happen to have a graphing calculator, what can you use to get that p-value? That would be the normal CDF. I'll put that in parentheses here. Normal CDF command. Okay, confidence interval. What is the formula for confidence interval? Well, the basic formula is x bar plus or minus z star times the standard deviation of the sampling distribution, sigma over square root of n. Okay, and what is z star? Z star is those particular values would give you certain percentages under the normal curve. Let's put that under the other comments here. For 90% confidence level, z star is 1.645. For 95% confidence, z star is 1.960. For 99% confidence, z star is 2.576. Okay, now let's go back up to our chart here. The next thing is when you're doing a hypothesis test, what is your null hypothesis? That is, the null hypothesis is mu equals some number. Like if maybe last year the population mean was 100 and now there's some new situation and you want to know if the population mean has changed. So you would say mu is 100 means the population hasn't changed, and then the alternate here, the next row down, the alternate hypothesis is mu is greater or less or not equal to, just depending on what your suspicions are or what the question is. And keep in mind, if you have a not equal sign, that's a two-tailed test. Let's make a little note of that here, two-tailed. Okay, last thing, hypothesis test. What is the test statistic? In other words, when you're doing your hypothesis test and it's time to calculate how far apart is your sample mean from the null hypothesis, that's a z. So you say the test statistic is z, and the formula is x bar. It's your particular sample mean minus the mean from the null hypothesis, mu subscript 0, divided by that standard deviation of the sampling distribution, sigma over square root of n. All right, and then back here under other comments, this is where you can put down any other miscellaneous things that don't really belong in any of these other rows. I would say under other comments, this is a situation that's not realistic, because you can't always assume your population is normal, and you can't always know what sigma is. Okay, so that's the idea, and then we'll just keep doing that for all the chapters. And so next is chapter 18. That was the chapter where you didn't necessarily assume a normal population. Sigma was unknown, and from now on, sigma will be unknown. So let's write that down here. Sigma is unknown, and we have one sample that's of quantitative data. So one sample, quantitative. Okay, so I recommend press the pause button for a moment and fill out all these rows yourself for chapter 18. Look in your book, look in your notes, write down your formulas and so forth. You'll get more out of it that way. And then once you're done, then press play again, and then I'll go through these for you, so you can check to see if you did it right. Okay, hopefully you've had a chance to write in all the details yourself. Now let's go over it so you can make sure you did it right. So in chapter 18, what were the conditions besides one sample and quantitative variables and sigma is unknown? The other conditions is you must have a simple random sample, and also the sample size makes a difference. The t distribution, which is chapter 18, is a robust situation. See, it's a robust distribution, meaning even if the conditions aren't met perfectly, the t distribution still works pretty well. So under ideal situations, you have a normal population, ideally normal population. But if your population is not normal, then under certain conditions you can still use the t distribution. So here's the condition. So if, and the author of this textbook says this: if n is less than 15, then make a histogram of your raw data, and you should have a unimodal and symmetric histogram. Now, of course, it's not perfectly symmetric. Nothing ever is. But as long as it's close, then it's okay to use a sample size less than 15. On the other hand, if n is between 15 and 40, then it's okay to have a skewed distribution. Skew is okay. However, you should not have outliers. No outliers. All right, and then the last part of this rule is if n is more than 40, then anything is okay. All right. Now, different textbooks have slightly different guidelines here. The general idea here is the bigger your sample, the more you can get away with. In other words, the smaller your sample is, the more close your distribution should be close to normal. And then the bigger your sample gets, the more skewed something can be, the more outliers you can have, and things like that. Okay, on to the next thing. Population parameter, same as chapters 14 and 15. You're trying to estimate mu, the population mean, when you're doing confidence interval, or you're trying to test a claim about mu if you're doing a hypothesis test. The sample statistics, same as the last chapter. You need x bar and n, but also you need s, because the population standard deviation is not known anymore. And so the best we can do is use s to estimate that population standard deviation. Okay, the sampling the standard deviation of a sampling distribution, well, it's sigma over square root of n, like we had in the last chapter, but we don't know sigma, so we have to estimate it with s. So it's s over square root of n. And then the author wants to call that a standard error instead of the standard deviation. All right, the sampling distribution is now a t distribution. And the reason, two reasons. One is we're not assuming normal populations anymore, because as we talked about in the conditions, if you don't have a normal population, the t distribution will still work. And also, we don't know sigma anymore. So t distribution. So what table, to look up p-values, what table do we use? We use table C. That's the t distribution table. Or if you happen to have a graphing calculator, it's the tcdf command. I'll put that in parentheses for those who have graphing calculators. Okay, confidence interval. Structurally, it's the same as this, except we're not using z, we're using t, and we're not using sigma, we're using s. So it's x bar plus or minus t star, and you get your t star from table C, times s over square root of n. And one more thing is t star depends on degrees of freedom. Let's put that under the other part. Degrees of freedom is equal to n minus 1. Okay, next row. Testing, null hypothesis. The null hypothesis is same as chapter 14 and 15. Mu equals something. The alternate is mu is less or greater or not equal to. And then if it's not equal to, then you have a two-sided test. Okay, the formula for the test statistic is now t. T is equal to x bar minus mu from the null hypothesis divided by s over square root of n. So you can notice a lot of similarities between these two, but there are some subtle differences here. We need s. That's the biggest difference, and we're using t instead of normal distribution. But as far as the formulas go, the structure of the formula is the same. Hypothesis test formula, x bar minus mu over s squared of n. It's the same structure. This is structurally the same as this, except we're using s instead of sigma. And the t stars are different because it's a different table, but it's pretty much the same otherwise. All right, so that's chapter 18. So tomorrow in class, on Friday, we'll do chapters 19, 20, and 21.